So hopefully we have a short meeting today, so it will be enough for internet connection. Okay, I would like to share the screen and start the exercise. Basically, I also would like to remind you, wait, what did I do? I didn't do what I wanted. I would like to remind you that you still have homework 4 that you should submit, homework 5, and today I publish homework 6. So basically you have something like 3 homeworks, and please finish at homework number 4 and 5. 6 is 5 was not so difficult, and 6 is also not very difficult homework.
L10 was a nightmare.
Which one? Which one was a nightmare? 3, 2? I think homework 3 was the most difficult. With regular expressions, it should be okay, no?
No, the problem was the L10. It was the difference between the number of zeros and ones was 3. That was it's. I don't know. I got something very long.
Yes. Everyone who built an automaton and used the algorithm got a long expression. But it's okay.
There's no.
I used yesterday I talked with the Hebrew group, so they asked me that they also had a long expression. So first of all, I told them, please use the properties, because even after you use the automaton and the algorithm, how you transfer automaton to regular expression, you still can improve the regular expression and make it shorter. And what I also did, I told them that you also can use some knowledge. For example, I know that if I have 0 and the 1 afterwards, I know that basically this combination doesn't add anything, and this combination doesn't add anything. Because for each 0, I have additional 1, so the difference, I didn't change the difference. So I told them, listen, you can also keep this knowledge in mind. Maybe you can improve your expressions. But it's okay, we will publish also the solution. And the solution, which is a transformation of the automaton to regular expression, will be accepted. It is okay.
But we won't lose points for not being the most the shortest.
You were asked to write the shortest, but sometimes you can't see the shortest possibility. So, for example, L10 is a good example for this.
Okay. One more question, just question 3 and 4. Do we need to show the entire way we got to the final question, or just the final question? The
No,
final answer.
you can only show the final answer.
Okay.
You can only show the final solution.
Great. Thank you.
All the way it's for you. Actually, it would be good for grade checker to show you where you had the mistakes, but we didn't ask. So if you submit only the final solutions and it's something wrong, they will write that it's something wrong, but they can't correct your way. Okay, guys, so we start with practice of unit 5, and it is actually a relatively small unit. And basically the question was, how do we minimize our DFA? And this question was asked already several times during the course. And the idea is to finally show you the algorithm. And that was the whole idea behind lecture 6 and the unit 5 that we studied. So what I did during the lecture, I defined what is equivalent states. So we can see that sometimes we have 2 different states at the automaton that actually can be merged, can be united to one state. because we can't find the separation word. So additional definition that I gave is separation word. For example, when I have some automaton, I can start with separation word epsilon, a zero length word, an empty word. When I separate between accepting state and non-accepting state. So they behave differently. Accepting state accepts the word, non-accepting state don't accept the word. Then we usually add additional letter and try to find the separate word of length 1. Then we continue with length 2 and so on until when we continue with the equivalence idea until we have 2 iterations, and during the 2 iterations we have the same equivalence set. So if in some iteration k I had, for example, 4 groups of states, and if in state k plus 1 I still have the set of 4 groups of 4 sets of states, so I know that I finished the algorithm. If I can't improve, if I can't find additional separation, I know that I should stop. And this was the idea behind the minimalization of DFA. So basically the idea is to start with your DFA and to build an equivalence states and continue with the algorithm until you can't separate any more states, and then redraw the automaton. And that is basically what we will do today. So please, this is an example that was given during the lecture, and we told that we will solve it in class. So basically, we are giving some DFA, and we were asked to construct equivalent class states to a given DFA. And then we would like to redraw this DFA. So let's start with the idea. I will remind you. We start with the equivalence set that we called it E0, because we are currently looking at the 0 length separation word. And we basically separate all the states to accepting states and non-accepting states. So I will have here Q0, Q1, Q3, Q4, rejecting states, and I have additional equivalence group, equivalence set with Q2. And this will be the first step of building equivalence classes. So now the idea, how should I continue? I can't separate Q2 because it's only one state. So if I have equivalence class with only one state, I don't need to continue with it. So I'm looking to this state where I have at least 2 states. And here I have 4 states, Q0, Q1, Q3, and Q4. So basically now I would like to find a separation word between 2, maybe 3, or maybe all 4 states. It can be given. So for example, if I'm looking at this automaton, I will tell you that A will be a good word. Why? Because Q1, Q3 with A, I move to Q2, to the accepting state, and Q0 and Q4 with A, I actually stay at the same class. So I already see that I can separate Q1, Q3 from Q0, Q4. But I only checked the input A. Maybe if I will check additional input letter like B, I will find the additional separation. Maybe I can separate between Q0 and Q4, or maybe I can separate between Q1 and Q3, because I already, for the letter A, found that the Q1 and Q3 for A will go to Q2, Q4 and Q0 for the letter A will stay at the same group. Please pay attention, it's not a self loop, it's the same group. So I'm not moving to the different equivalence class. So I would like to check what should I do with input B. So I'm once again looking what happens. Q3 and Q1 for input B. I go to the state Q4. Q4 for the input B, I also stay in Q4. And Q1 in input B, I move to Q1. So basically for input B, all the states stayed here at the same group. I couldn't separate their behavior. So now I can write the definition of E1. So E1, the meaning of 1 that I found a separate word of the length 1 would be, I can separate Q1 and Q3 to new equivalence class. I can still keep Q0 and Q4 as the same equivalence class, and I already had Q2 as an additional class. Any questions till now? Okay. So the next state, when I will look now at the separation word of the length 2, but I actually don't need to look at the length 2, I can take additional letter of the alphabet, and the idea is, can I separate Q1 and Q3, and can I separate Q0 with Q4? If yes, then I have a new equivalence classes, and I can continue with the algorithm. If I can't separate, I should stop. So basically, I can start with Q1 and Q3, but I already know that I can't separate them. Let's talk why I can't separate Q1 and Q3. Q1 on input A lead Q1 on input A and Q3 on input A went to the same state, Q2. So for additional letters, they won't behave differently because I will continue from Q2 and it will be the same behavior.
And same for B, right?
The same for B, exactly. In this automaton, it's the same for B, since we have Q4. And once again, for the second, third, fourth additional letters, we can't continue anymore. It will be the same state. So I actually can see already in previous state that I can't separate between Q1 and Q3. They will be together forever, because for input A and for input B, they lead to the same state. But I will check now what happens with Q0 and Q4, and I will use only one letter of the input and the computation of previous E state. So I will use E1 class or E1 stage, and I will check if I can separate between Q0 and Q4. So let's see. Q0 on input A leads me to Q3. So please pay attention. Q0 on input A leads me to the group Q1, Q3. And Q4 for input A leads me to Q4. So I stay here. So I can stop because I found the separation word between Q0 and Q4. And there is only two states. I already separated them. So what I need is only to rewrite the definition. So E2 will be Q1 and Q3 are still together. Q1, Q3. I managed to separate Q0 from Q4. So Q0 is now a separate class and Q4 is an addition class. And we also had Q2. Okay, I can't stop right now. I still have to continue with the algorithm because the algorithm stops only when we have EK that equals to EK plus 1. When we have an iteration that doesn't add us any classes, we know that we finished with the algorithm, because if we will add additional letters, it won't help us. We already were stuck in K iteration. So basically, let's see how we draw E3 and if we have any separation for E3. Once again, I'm only interested in groups that I can separate, and here it's only Q1 and Q3. I can't separate anyone anymore. Q0 is alone, Q4 is alone, Q2 is alone, that's it. And for Q1 and Q3, we already know that Q1 and Q3 on A go to Q2 the same state, and on B they go to Q4 the same state. So I can't separate them. So basically I know now that E2 equals to E3, and I can stop with the computation. So the next question, I would like you to draw the minimized DFA after you computed the equivalence class state. So take your time. Wait, I will move to this. This is our solution. This is oops. This is E2.
You want us to draw it? And
Yeah, okay. It will take you something like 2 minutes.
Where's E3 though? There was a final one, no? Or it, or...
2 is the final one.
Oh, okay.
3
And what was the
3? You know that you stop. E2 equals to E3. That's why we stopped.
okay? And Q0 is the initial state. Okay.
Yes. Okay, did you finish?
1 second.
Okay.
Yeah, okay, I'm done.
So first of all, you start with your classes. So you will have 4 states in your new automaton. Q0 state, Q4 state, Q1 and Q3 united, and Q2 an accepting state. Q0 is initial state. From Q0 with input A and B, you will move to Q1, Q3. Q1 to 3 on A will move to Q2, and Q1, Q3 on B will move to Q4. Q2 on input B will return to Q1, Q3. Q2, why I didn't have Q2 with A? Sorry, I have to complete this. Q2
To
on
Q4.
input A will go to Q4. Yes, definitely. Okay, here we will move here with A. And Q4 is actually a trap stay. We stay here forever with any input. So now we have a minimal DFA. So basically, until we reach the end of the course, when you are required to build a deterministic finite automaton, usually you are required to build the minimal DFA. So you have to use this idea of equivalent states and to improve your automaton. Okay. Actually, this was the only question during the lecture, but I've added additional automaton just to practice. And basically, that's the whole idea behind also the homework. You will be given several automatas, and you are required to build minimal DFA and also to check some claims and to see if those claims are correct. So now, since we did one question all together, I would like to give you the time, and you are required to construct equivalent class states to given DFA. And that's what you will start with. Then I would like you to answer the question, which K actually holds the property that EK equals to EK plus 1. And the additional question, how many states were united? So you will also answer this question. So please build E0 for this automaton. I think E0 is very simple. So E0, you just separate between accepting and non-accepting states. So we have a class Q3, and which was an accepting state, and you have Q0, Q1, Q2. So please try to build E1. Once again, in E1, you can only separate a group, so you are only interested in Q0, Q1, Q2. I'm just asking if you finished.
Finished what, E0 or the entire thing?
E1.
Oh,
E1. Will give additional moment. Thank you for answering. Okay, here we have 3 input letters. So you have to check all 3 input letters. Maybe you can separate Q0 from Q1, Q2, and maybe you can also separate Q1 from Q0, Q2, and maybe for additional letter you can separate Q2. So maybe after this state you can separate Q0 with Q1 and with Q2. So sometimes separation, it's not splitting into 2 parts. Sometimes it can be 3 parts or 4 parts. It depends on your language and on your automaton. So let's check. I can see that Q2 with C and Q1 with C, I go to accepting state, and Q0 with C, I stay here. So I already know that I can separate Q1, Q2 from Q0. Q1, Q2 with C, I already found that I can go to Q3. Q0 with C stays at the same group. I can check additional letters. Maybe the behavior will be different. So I can see that Q1 with B goes to Q2. Q2 with B stays at Q2. Q0 with B goes to Q1. So here we have the same behavior. Q0, Q1, and Q2 for the letter B stay at the same class. So I can't separate between them. But we have also an input letter C. So if I check Q2 with, sorry, C we already checked, A. Q1 with A goes to Q0, Q2 with A goes to Q0, Q0 with A stays with Q0, so A also doesn't help me. I go to the same state, so I can't separate. But since the letter C gave us an answer, we can redraw now the E1 group. And E1 will be Q3, an accepting state, as it was, the same class. Q0 can be now separated to the new class. And Q1 and Q2 are still together. Okay.
In every iteration, we can look only on the groups, right? If you have separate Q0 and Q3, we can just ignore them, right?
Yes. You already don't have to. If you have a group, a class with only one state, that's it. You don't continue with it anymore.
Great, thanks.
Okay, now I will give you a few moments, and the question is, please compute E2. Okay. Okay, basically finished, everyone finished E2. Can you separate between Q1 and Q2?
No, they're the same.
No, they're the same. We actually saw it in the previous state that Q1 and Q2 on letter B went to the same state. Q1, Q2 on letter C went to the same state Q3. Q1, Q2 on input A went to the same state Q0. So they have to behave the same. So we actually have the same set. So we have E2 that is actually E1. And now we know the answer to this question. What is the minimal K which holds that EK equals to EK plus 1? The K is 1. That means that after 2 iterations of the algorithm, we finish the computation. Okay, now the next question. How many states are united?
2.
2 states, Q1 and Q2 are united. Sometimes when you have, for example, several groups, for example, I will have Q1 and Q2 united, let's say, and I will have Q4 and Q6 united. So sometimes when answering this question, students find it difficult to, because it's not that 4 states were united. It is 2 states were united twice. So basically, I don't know, just formulate your answer. Please write that two states are united twice and just show maybe those states so the answer can be clear, because not 4 states are united, because it's 2 states that united into one group and additional 2 states that united to the additional group. Okay, so the last stage, please build the minimum DFA equivalent to this DFA. Okay, use your groups to construct. I can keep original automaton here. So basically, once again, you start with your classes and then just complete your drawing for each input letter. I'm just checking if you finished. Oh, okay, everyone finished, so I can show the final automaton. So Q1 and Q2 are united, Q0 is initial state, Q3 is the next state, and then we just have all the input letters. We have A, B, and C. So we have Q0 with the A, B, and C, Q1 with A, B, and C, and Q3 with A, B, and C. And that's it. Any questions? We finished our practice for today. I would like to remind you that you still have homework 4. Students who didn't submit, please submit it. Homework 5 is due till tonight. So basically you have to finish it. And homework 6 is already published at the course website, and you can start working on it. And basically next week we will start talking about non-regular languages, and we will continue to new models. Any questions?
I have a question.
Mm-hmm.
There's no direct way to move from a regular expression to DFA, right? You have to go through the NFA and then translate it? Okay.
Yes.
Connecting to his question, what if I see the DFA? Do I have to go to the entire process, or can I just?
The question, okay. 2 answers. If you are not asked to show the way, you can go to DFA. That's what actually I showed you during the practice exercise last week. That I can use my mind and I already can improve my drawing and not start with the whole idea that I have regular expression and then I add the states or different way. So if you are only asked to show the final answer, you can do whatever you want, but the algorithm starts with NFA.
Okay, so it's just connected to the homework. I did it. I did one question. I did just direct, but you didn't ask for the entire way, so it's okay.
No, we didn't ask for to show all the states, so you can go directly.
Great. Okay, thanks.
Additional questions?
Yes, I have a general question, not about today's class. When converting an NFA with epsilon transitions to DFA,
Okay.
so I find it very confusing what should I do with the epsilon closure? When should I consider it?
After you, okay, at each stage, after you've built additional states, you now, okay, let's say that I have partial automaton, okay, that I already started to draw. I have some Q0, and here I have, let's say, Q1 and Q4 united, and maybe this would be an accepting state. So now you have to find where you go for each input letter. And let's say that our alphabet is A and V. So I check where I can go with Q0 with A. And let's say that with A, I have a new state Q3. And I used only one A. Now, when I have Q3, I add epsilon closure. And if Q3 with epsilon can move to additional states, let's say that Q3 can go to Q1, then I add Q1 to this state. Now you check Q0 with B, where you can go, the states, specific states, and now you do epsilon closure for those states, and you unite your answers. Q1, Q4, you check where you can go with A from Q1, with A for Q4. You unite where you can go with A. And now you perform epsilon closure on this group. And if you have additional states, you add them.
Okay, so I do it every time I merge
Every
in a
time,
state.
one letter, go to all the states you can go, unite those states, compute epsilon closure for these states, add additional states that you can reach to your group.
Okay, great, thanks.
So each time, first compute, use the letter, specific letter, input letter, then epsilon closure.
Oh, I didn't understand, Rena. Can you
Okay.
go over it again? The same question.
The same question?
Yeah.
So basically, if you have some state, and let's say that it's already United States, and you need to compute where you can go on input A, you compute where you can go on input A from Q1, and let's say from Q1 I can reach Q2. And where you can go on input A in Q4, let's say that I stay in Q4. Now you have to compute epsilon closure of this state. And if epsilon closure of Q2 leads you to additional state Q1, you add Q1. So first of all, epsilon closure, I stay in Q2 and Q4 because I can use epsilon closure 0 times. I can use epsilon 0 times. If Q2 with epsilon can also reach Q1, I also add Q1 to the answer. If Q4 can, with epsilon transition, can move to Q2 and can move to Q3, I will add Q2, but Q2 I already have, and Q3 to the answer. So now when I draw where I go from Q1, Q4 on input letter A, I go on input letter A to this state, which is actually A letter once. A letter once is Q2 and Q4. And additional states that I reach with epsilon transitions only.
But you increased it. You said you can only decrease the epsilon closure.
No. We are talking about how you transfer NFA with epsilon to DFA. With epsilon transfers, you only can add additional state.
Mm.
You can't minimize. No,
Okay.
no way.
Okay.
You only can add additional states. Sometimes you stay with this group only, but usually you have additional places to go.
I'm not sure about the pairs, about selecting the pairs to go to for the next iteration.
The pairs to go, I usually tell you, please start with Q0. You have to compute here, you have to start with the epsilon closure of Q0. Let's say that epsilon closure of Q0 will be Q0 itself.
Mhm.
So you start with Q0, and now you have to compute this algorithm for each input letter, sigma 1 and let's say sigma 2. You compute directly where you can go. Let's say that here sigma 1 was not defined, so I have even an empty set, and Q2 lead to Q1 and Q4. But now you have to compute epsilon score here of an empty state. It doesn't add anything, but an empty epsilon closure for Q1 and Q4 can add you additional states here, maybe. So you have to compute E. E is epsilon closure for the Q1, Q4 that you've reached. And if you have some additional state, first of all, you have Q1 and Q4 if you don't use any epsilon transitions.
Yeah, no, and I understand the epsilon conditions. I just didn't understand how do you select the pairs to check against? Because I just went over all the pairs when I did it.
You don't need it. For example, let's say that I have Q1 here, not an empty. And here I have Q1 and Q4. So I already computed the answer for Q1. So I only need to add the information that Q4 adds me. So usually you have 1 or 2 or 3 steps that you have to compute everything. Later you can unite your answers because the answers are already there. Because you usually already computed where do you go with Q1, you usually already computed where do you go with Q4. So if you have now Q1 with Q2, at least for Q1 you already know the answers, so you only have to add Q2 and so on.
Okay.
But basically the algorithm for computer is just draw all the sets, the power set of Q, draw all the transitions, delete unreachable state. That is the algorithm for computer. But then you have to draw the power set of your states. So let's say I have 5 states in the original automaton, I will have to draw 32 states. So for computer, it's okay. For us, it's not so good because majority of states will be deleted later because you can't reach them from Q0.
Yeah, that's what I asked, how to minimize the checking, because if you have 6 states, it's a lot to check.
Use the algorithm like we did. Start with epsilon closure of Q0 and continue with states that you have. Don't draw everything because otherwise you do a lot of technical work that you don't need.
Okay.
Okay, additional questions? If not, so we finished. Have a nice week.
Thank you.